Uh, Good evening, good afternoon, and morning, maybe good night. Everyone.
All time skills.
Welcome to this session here, second day. It's a second. This is the second time parallel session of this day. So there are another hall A, and this is hall B. So I welcome every speaker here and as well as the coordinator of this session, Dr. John. He is one of the eminent scientists in India, basically in global modeling and data assimilation. He is the senior most scientist there in the data assimilation group of NCM at WM, India. And he is also pioneer. He has done some pioneering research in mesoscale modeling in India. So, sir, John, sir, now welcome to this session. Now it is up to you to coordinate the whole session. There are, I think, all speakers are available, or maybe one or two speakers may not be there, but they may be presenting directly their presentation. So, and sir, for this questions and answer, there some question and answer will be directly from the attendee here, but some of the questions may come from the live YouTube streaming. So that will be provided directly to you through chat box or through our admin staffs or support staff. Dr. Buser most probably there, sir. So now up to you, sir. Over to you.
Thank you, Anandas. Thank you for the organizers for giving me the opportunity. In this session, actually, there are 6 presentations are scheduled, but currently I think 5 people are available. And the first presentation is by Professor Andrew Turner of the University of Reading. I think he has 2 presentations. So I welcome him for his first talk. Can you start your presentation now?
Can you see my presentation full screen?
Yeah, yes. Actually the duration is 12 minutes. So if you exceed 12 minutes, I will give an alarm.
Yeah. Yeah, I think that was including questions anyway, but okay, sure.
Yeah.
I'll start then, if that's okay.
Yeah. So, please start.
This is the I'll just put my laser on. This is some work concerning our 2016 field campaign in India called the Encompass project, which was a project that was funded by MOES in India and the Natural Environment Research Council in the UK. It was led by myself, Andy Turner at University of Reading, and Professor Butt at the Indian Institute of Science. I hope you'll forgive me for not displaying all of the other scientists that were involved in this campaign on the screen, because I can't fit them on. There's so many of them. But just to give you a clue as to how many scientists there are, it's basically all of the names that are listed on our paper here. So a great deal of work by a lot of scientists, both in India and in the UK. And one of the main sort of cruxes of our field campaign was that we were flying a research aircraft, which was this one here, over India for a period of about 6 weeks. Okay, so what motivated us? What were we interested in for our field campaign? We were really interested in how contrasts at the surface, how they modify the overlying atmosphere and how they might modify convection. So we're interested in coastlines, in the orography patterns, so particularly the West Ghats. We're also interested in something that's not been studied so much, which is gradients in soil moisture, and they might come from rainfall, or they might indeed come from irrigation patterns. And the green colors on this map here are just giving you some idea of some of the irrigation patterns in India. So what about our flight strategy for this field campaign? So we were flying in this aircraft here, it has 4 engines. It's a UK atmospheric research aircraft, and it can seat around about 18 or 19 scientists in the back. So it's not just instruments. The scientists are actually on board taking measurements. So we wanted to do 2 different types of regional sampling during our field campaign. One of those was to base ourselves in northern India, in Lucknow, and we were flying to the east and to the west in order to look at contrasts across the country as the monsoon evolves in time. And of course, as we know, the monsoon passes across the country like that. And secondly, in southern India, we were based in Bangalore, and again flying to the east and west and sampling these contrasts across the coast and across the Western Ghats mountains. So these were the map of the flights that we did from our 2 airports, from Lucknow and Bangalore. And the idea was very much to repeat some of these flights at different times in the monsoon in order to sample contrasts on multiple occasions. And particularly from Bangalore, we were flying across the Western Ghats. However, Encompass wasn't just about flight observations. We also made some significant advances in flux tower and surface fluxes measurements, and we installed a number of eddy covariance flux towers at the different sites you can see here. And the reason for doing that is because actually, certainly at the time, there were quite a paucity of measurements of surface fluxes in India using reliable flux tower measurements. So I'm just going to present 3 very brief cases or examples of some of the science and some of the papers we've outputted. I'm not going to go into much detail at all because we don't have time, but you can look at the papers for more information, and also you'll be able to get the data if you want it. So the first of them is thinking about surface flux measurements, and there was a paper on this that Professor Batt led in the 2020 issue of the Quarterly Journal. And this is just to really give you an idea of what was going on here. So you can see that obviously that's our different flux sites. They have very different surface and vegetation characteristics. This graph at the top here is just showing the evolution of sensible heating and latent heating at 2 different sites, Jaisalmer and Samastipur, and those have very different surface characteristics. So one is based on sandy soils and one has kind of standing water, so almost like a paddy rice environment, and they give rise to completely different flux partitioning. And the information from these flux towers is going to be very valuable for us firstly for looking at land surface models in standalone mode and studying the fluxes. And what we tend to find is that the fluxes are nowhere near strong enough in these models. And then, of course, also look at them in GCMs and try and think about how the boundary layer and convection might be responding to those surface fluxes. And the ultimate aim really is to inform parameterization development and improvement for convection schemes. And just an idea at the bottom here, you can see that between these 2 different flux tower sites, there's really quite different regimes going on. So there's 2 distinct regimes at the Jaisalmer site, either LH dominated or sensible heat dominated, but not at the Samastipur site. So very quickly, I'm going to go through a case study of some flight measurements from northern India. And this was in some work by Emma Barton of the UK CEH, again published in Quarterly Journal in 2020. And what we were interested in was flying at low levels across soil moisture gradients and trying to measure and then later model what happens in the boundary layer and in the creation of shallow convection and deep convection. So this was the flight we took, and actually this is an indication of the fact that you can get a whole paper, an interesting study from a single research flight. So this particular flight on the 30th of June 2016, we flew west from Lucknow here over towards Jodhpur, and then we flew back at very low levels in the atmosphere our return leg was at an average height of 191 meters above ground level, so incredible. And what we found in this study is that steep gradients in air temperature were correlated with wet and dry transitions in the soil moisture, and they eventually give rise to local convergence. And you can get a demonstration of that here. So this is the flight track overlaid from Lucknow westwards. The field that we're seeing here is something called the GPM satellite polarization ratio, which is a proxy for soil moisture. And you can see it shows boundaries between wet and dry soils. And from our observations from the flight, we knew that this particular soil moisture contrast over towards the east, this was caused by irrigation practices, whereas the one in the west was caused by rainfall that had happened a few days before. So next, if we just look at the boundary layer temperature, so I think this was the temperature at the 925 hectopascal level in ERA interim or directly on the flight, you can see on the track here. And what you see is that there are very sharp contrasts in the boundary layer potential temperature associated with those surface contrasts in soil moisture. And what we'll see on the next slide is at those locations, at the sharp contrast locations, you see strong patterns of convergence of the wind. And so you get that idea here. The white arrows are showing the wind vectors as measured from the flight as it's flying through the boundary layer. And you get this idea of strong convergence over that soil moisture gradient. And what we eventually discover, and you can read the paper for more details, is that initially shallow convection develops there. And then later in the day, through the diurnal cycle, as the land heats up, you get deep convection and convective storms. And the reason we're interested in this is because a lot of previous work has shown the importance of this mechanism for convective initiation in West Africa. But because these mesoscale gradients are really quite small, it's unlikely that they're represented in GCM scales. And so we need to develop better parameterizations and have better land surface sort of ancillary inputs in order to measure this. So our second flight case study that I just want to show you is a paper by Jennifer Fletcher et al. Based at the University of Leeds. This is based on our flights from southern India, from Bangalore over the Western Ghats. And this is a Hofmüller diagram, time going up the page from the 21st to the 28th of June 2016. We've got the coastlines of India marked on in these solid lines here. And we did a series of several flights through that week based in southern India across the Western Ghats coastline. And what we see in the precipitation diagrams is that there were really some distinct regimes of offshore convection shown here, and then a bit later in the week, some coastal convection, or what we now call the onshore convection, very close to the Western Ghats. And we hypothesized a framework, and there's a cartoon shown here from that paper, in which somehow these regimes of onshore and offshore convection were controlled at the large scale by a dry intrusion. And subsequent work led by Kieran Hunt, who's presenting a talk on this on Friday, has shown that the behavior of these regimes is strongly controlled by the boreal summer intraseasonal oscillation, and you can demonstrate it on this type of phase diagram, but see more on that in his talk. So I just want to summarize there to the end of my time. So the Encompass field campaign was based on 22 research flights, flux tower measurements, and other instrumentation, particularly at IIT Kanpur, where we had a super site. A lot of that data is freely available at the CEDAR catalog website there. We've already demonstrated that the observed flux partitioning is not well represented in models. We've shown the importance of soil moisture patterns to the monsoon storm development. And we've also demonstrated that there are scale interactions connecting large-scale controls to Western Ghats precipitation regimes. So it gives some predictability. And also demonstrated, but not described here, we've made a new paradigm for the monsoon onset, and we explain why it propagates to the northwest in a series of papers. And I think going forward, we need renewed efforts for greater sampling and long-term observations aligned with model testing and development in order to improve forecasts. So thank you very much for your attention, and thanks once again to our funders at the top there. And we do have a special issue in Quarterly Journal that has a lot of our papers. There's a lot of other papers as well outside of that. And if you're interested in the field campaign or any of the papers, please get in contact and I will pass that on. So thank you. I'll stop there.
Thank you very much, Andrew. If any question is there, he has his presentation was very nice, and actually this 2016 Encompass campaign results. So it's a very valuable results are coming from this field campaign, and he has presented some of the results. And if any questions are there, I think we have one or two questions can be. His time is there. Okay, then let us thank Andrew for your nice presentation. Let us move to
very much.
Let us move to the second presentation. It is from the Sachin Deshpande from IITM. You can start your presentation now.
Yeah, can you see my presentation in full screen mode?
Yeah, it's fine.
Yes. So good
you may
evening,
please start.
everyone. I'm Sachin Deshpande from IITM Pune. The title of my presentation is Analysis of Convective Organization over the Monsoon Zone using Radar Observation. And I would like to acknowledge my colleagues from IITM. I will briefly start with giving the background on the monsoon core zone and atmospheric research stage beds. Monsoon trough over the central India, which comprises of the monsoon core zone, is an important central component of the regional climate system. Detailed atmospheric measurements over the monsoon zone are important because this is the region where most of the synoptic scale disturbance that forms over the head Bay of Bengal and passing over the central Indian continent. Even though these are frequent measurements, all the detailed atmospheric measurements were overdue. So considering this importance, an atmospheric research test bed in central India is established by IITM MOES at Silkeda, which is the site 50 km north of the Bhopal, for better understanding on the processes governing the monsoon convection, including its diurnal variation and land atmospheric interaction over the monsoon core zone. This is the planned layout of atmospheric research test bed in central India. It is spread over the almost 100 acres, and ARCTCI will have wide set of remote sensing and in situ instruments to provide continuous observations of convection, clouds, precipitation, soil moisture, radiation, microphysics, and many more. So all these co-located and concurrent measurements from multi-instruments provide the key resources for validating the CRM and GCM using both the statistical and process-oriented approaches. So we know that atmospheric precipitation falls from a spectrum of clouds, and radar is commonly used to characterize the nature of precipitating clouds. These categories imply the nature of vertical air motion that produces the precipitation, along with the divergence and latent heating profiles in the atmosphere. And this deep convection in the Earth atmosphere can be scattered across an area at times, but it can also be spatially clustered in one place. So this varying spatial distribution of convection can be referred to as the organization or clustering, and this clustering is well correlated with the severe weather. So hence the quantification of convective organization or clustering becomes important. And this deep convection is frequent in monsoon core zone, which produces the widespread and heavy rain. So focusing on the clustering aspects of organized convection, in the past, different matrices or indices have been developed to quantify the strength of organization clusters. For example, simplified convective aggregation index for organization, convective organization potential index, and all these scalar indices are based on the two-dimensional binary fields such as the radar reflectivity, precipitation, OLR, and among all the instruments, ground-based radar data with its high spatial and temporal resolution So they have 1 to 2 kilometer spatial resolution and 5 to 10 minute temporal resolution. They provide the best observational tool to study the convective clustering with continuous time sequence during convective life cycle. So this is the, as part of this ARTCI, recently this C-band polarimetric radar was installed. The beauty of this radar is that, so this is a polarization radar. So we can have extra information on hydrometers, size, orientation, shape by transmitting the horizontal and vertical polarization in the atmosphere. So all these pictures shows the chronological events of events from the first day of construction, that's what started in 13 July 22 to the first radar observation. And during monsoon 2021, so we have collected very highly time resolved 6-minute 3-dimensional radar observation. So this is an example of a 2-kilometer CAPI of a Doppler and polarimetric variables of a C-band radar. So you can see a region of intense convection where the reflectivity is more than 40 dBc, and these regions are associated with the high ZDR values, which indicates the presence of large size hydrometers. And we can see that there is a nice region where you can have the positive KDP that implies that there is an increase in the size and concentration of raindrops. So that is indirectly related to the increase in the rain rate. And using this, all these dual polarimetric variables, so we can also have the hydrometer classification, and you can see that there is a existence of hail and graupel. Okay, so from among the many data set, we have selected one case study of 4 to 6 August 2021. So 6-minute radar volume scans were converted to a 3D Cartesian grid. So horizontal domain of 300 kilometer, 300 kilometer with horizontal grid spacing of 1 kilometer and vertical grid spacing of 0.5 kilometer. Then we applied a rain type classification algorithm of Powell to the radar reflectivity field at 2 kilometer to classify each grid point into 6 different categories, like a convective, isolated convective core, isolated convective fringe, stratiform, mixed, and weak echo. So this is the advanced version of a rain type classification as compared to the Steiner algorithm. So following that, the scalar matrix of convective clustering, like a SCAI, is applied to radar identified convective objects. So in order to objectively quantify the degree or the strength of convective organization within the radar domain during those 3-day event period. So this is the animation which shows the precipitating cloud system that was observed during this period. So there are 3 animations. So the figure to the left is the 30-minute satellite brightness temperature with less than 241 Kelvin, whereas the middle panel shows the 30-minute C-band radar reflected at 2 kilometer, while the rightmost panel shows the 6-minute, so which is a very high resolution radar maps. So what we can see is that there is a large scale feature which shows that there is a westward or northwestward propagation of a cold cloud system. Whereas from the radar, we can see a very nice mesoscale feature like a deep and intense convection. And there are families of convective cells. If you notice carefully, there are family of convective cells. They are organized in time and space, and that results in a spatially extensive convective system. So all these details are captured by the radars. So this is the quasi-vertical profiles of a C-band radar variables. So this is nothing but a height versus time representation of QVP of different variables taken at a 10-degree elevation. So each figure illustrates a QVP evaluation. Also, these are almost 60 hours of observations, which have 600 vertical profiles, and it reveals the complicated internal structure of a precipitating system. So what we can see that there is a well-defined signature of a melting layer or a bright band at around 5 kilometer in the stratiform cloud, and which is characterized by elevated reflectivity, also elevated ZDR, 5 dp, and there is a sudden decrease in the rho HV around the 5 kilometer level. So we can see that there is a high resolution representation of a melting layer. There are some undulations are seen. So this insect plot shows the signature of undulation within this melting layer. So you can see a very nice and detailed structures of the melting layer. So what we have done here, we added the wind information. So So using the velocity azimuth display, we can estimate the wind velocities, and you can see the westerly low level jet is nicely depicted here. So this is another advantage of having the wind information in absence of a wind profiler. So this is an evolution of reflectivity at 6 minutes, the rain types from the radar observation, and this is the 6-minute hydrometer classification. So you can see there are a range of different rain types: stratiform, convective, mixed, isolated convective core, isolated convective fringe, weak echoes. And here you can see the radar echoes. These are the estimated hydrometer types in the precipitation area into different rain types. So you can see the whole bunch of information right from the rain type classification to the hydrometer classification is nicely. So you can see there are lines of thunderstorm or the squall lines or the MCS you can see, and then there is a embedded convection within the large scale stratiform region is also nicely captured here. So this is the hourly time series of rain types during 4 to 6th August. So what we can see that the stratiform type has the largest percentage occurrence amongst the all types, which is followed by the mixed, the isolated convective fringe, the convective and isolated convective core. So these are the hourly times, even though we have this similar information at every 6 minutes. So let's see what is the observed structure of various convective categories. Okay. So this is the convective, mixed, stratiform, isolated convective core, and isolated convective fringe. So these are the reflectivity CFADs. So the convective CFAD shows that there is a presence of deep convection with reflectivity near 4 km, and below shows a value of greater than 40 dBz. Whereas the stratiform, there is a presence of a bright band. Bright band is clearly seen here. The mixed type, which are the echoes surrounding the convective cores within the 5 to 10 kilometers. So it has a characteristics of both convective and stratiform. Since it is based only on the reflectivity, so we cannot have a clear separation. And then there is an isolated convective core. So these are the cores of developing shallow and isolated convection. And then we can see this is the isolated convective fringe. So these are the echoes associated weak and decaying convection, and which surrounds the isolated convective cores. So this is how we can identify the different rain types and see their vertical structures. So this is the hourly time series of convex clustering matrix. So we have used the simple aggregation convective index, which focuses on individual convective objects and measures the aggregation by taking into account the number of convective objects n and the average distance between each pair of objects. So within the radar domain, so we have a radar domain of 250 kilometer, 250 kilometer, and then we identify different convective types and the number of convective types, number of convective objects, and average distance between each pair is estimated, and then we get one scalar quantity. So the advantage of having this cluster matrix is that it gives a numerical quantity, so that we can identify or measure the amount of convective clustering in a numerical quantity. So this is the SCI, and on the middle panel you can have a number of convective objects, and this is the distance between each pair of the objects. So evolution of this SCI is similar to that of n, because the variation of n is much larger than the D0. And then this is the scatter plot between the number of convective objects and the distance between the pairs of convective objects, and that we can see that as the number of convective objects increases in the domain, so there is so the distance between the individual objects increases. Okay. Then this plot describes the examples of radar scenes. Okay, so at given times, these are the selected times, and how the different parameters of the scaling matrix like n, D0, and SCI varies for different times. So this SCI describes the strength of convective organization for each snapshot of a radar volume with a numerical quantity. So by having this SCI information, you can quantitatively tell the strength of the organization or the degree of the organization that has taken place within the radar domain. So what we observe here is that the smaller the SCI, the more the convective clustering. So if you see the
Can
picture,
you please conclude?
yes, picture D and F. So you can see that as convection becomes more aggregated, cloud elements merge into fewer elements. That's the smaller end and that are more clumped together. So such type of radar convective clustering, which is at the scale of GCM grid box, can serve as an observational basis for quantitative comparison to convection organization in convection scheme. So highly time and vertically resolved seapole radar observations were collected during 2020 monsoon 2021, which provides a useful information on convective and microphysical processes. Special distribution of convective elements is used to quantify the degree of convective organization, and we will extend this study to include more cases with more matrices and relate the observed convective clustering to the vertical structure of clouds and the large-scale environment. This type of radar-based convective clustering can serve as an observational basis for quantitative comparison to the convective organization in convection schemes of model. From monsoon 2022, the radar observation will be augmented with K-band cloud radar, micro MWR, micro rain radar, ceilometer, and disdometer observation in order to obtain an integrated dataset from concurrent and co-located multi-instruments. With this, I stop here. Thank you.
Thank you very much, Dr. Sachin, for your nice presentation on the convection using the polarimetric radar data in the monsoon core zone. If any questions are there, only one question is possible. So then let us quickly, we can thank again Dr. Sachin Deshpande, and let us move to the next presentation. It is by Dr. Nirupam Karmarkar. So can you please share the PPT and start the presentation?
Yeah. Can you see the screen now?
Yeah, but yeah, fine.
Yeah.
You can start.
Yeah. Hello. Hello, everyone. So I'm Nirupam. I'm from IITM and NCMRWF, Ministry of Earth Sciences in Delhi. So I'll be presenting my work on dynamics of northward propagation of convection over Arabian Sea and Bay of Bengal and different aspects of, what are the differences in the northward propagation characteristics over these two ocean basins. My collaborators are Dr. Susmita Joseph and Dr. Sahai from IITM Pune. So the motivation and objectives are as follows. If you look into the time mean rainfall over Indian region, you can see that a large amount of rainfall is seen over the northern Bay of Bengal and the vicinity of Western Ghats over the Arabian Sea. And if you look into the northward propagation of rainfall in these using the TRIM rainfall data, you can see that convection develops over the equatorial Indian Ocean and gradually propagates to the foothills of the Himalayas in about 30 to 60 days time scale with a northwest southeast oriented tilted structure. And this eight phase composite diagrams actually shows that characteristics. And this has been shown in many of the earlier studies in literature. Now, the problem is the capturing this northward propagation of ISO in the numerical simulations or the models, dynamical models, is realistically, this is a challenging problem, and we wanted to look into the dynamics and how this dynamics is represented in different models. To understand that, we need to frame a diagnostic. So to do that, we actually did this study, and we have present here a diagnostic that helps to understand the different dynamics of this northward propagation, and that can help evaluating the model simulations. So here in the panel A, I'm showing you two different regions. One is over Arabian Sea, this box, and one over Bay of Bengal, this box, 10 degree, both are 10 degree by 10 degree boxes, and I'll be presenting some of the results in the subsequent slides that actually presents the northern propagations over these two boxes. Now, to understand better about the northern propagation, we refined our data set into just strong convective events based on normalized rainfall anomalies over these two ocean basins, Arabian Sea and Bay of Bengal. And then look into the lag latitude diagrams, basically the Hofmuller diagram based on these strong convective events. So basically, this 0 means the day when there is a strong convective event. It shows that maximum amount of rainfall over Arabian Sea, and similarly over Bay of Bengal. And this minus days, lag days, implies the days before that strong convective event, and the plus lag days basically is the days after the strong convective event. So it can be seen in color. It is the rainfall in both the panels, and it can be seen that the northern propagation of rainfall is much faster over Arabian Sea as compared to Bay of Bengal, which basically explains the northwest southeast oriented tilted structure during the northern propagation of rainfall. Now, in the contours, we are showing you the vertically integrated vorticity, the relative vorticity during these strong convective events over both the ocean basins. Now, it shows that the vorticity is kind of aligned with the rainfall structures, but has a lead of almost 1 to 2 days over Arabian Sea, and it shows a leading nature over Arabian Sea, but over the northern Arabian Sea, it kind of breaks down the communication between the vorticity and rainfall kind of breaks down over the northern Arabian Sea. Now, the genesis of barotropic vorticity to the north of an existing convection is essential for northern propagation, and it has been shown by a few of the previous studies, such as Jiang et al. We actually further investigated this development of barotropic vorticity to the north of convection using a vorticity budget equation. Now, to develop that vorticity budget equation, we start from the horizontal momentum equations. These notations are basically as usual, and U and V are basically the horizontal and meridional winds, meridional winds, and assuming that that we have a background wind speed and an interseasonal anomaly, and removing all other fluctuation terms, we can show that the development of barotropic vorticity, or the tendency of barotropic vorticity, can be written in terms of advection term, stretching term, tilting term, and the beta term, where the primes are basically the interseasonal anomalies, and the terms with over bar basically represents the background wind. So the interseasonal barotropic the generation of vorticity tendency can be written in terms of four of these terms. Now, we individually check these 4 terms and try to find out what basically governs this development of vorticity to the north of an convection. Now, if we look into the advection and beta term over these 2 ocean basins, we found out that the advection term does not really play a role in showing you actually capturing the northern propagation of rainfall. Now, in these panels, the rainfall is basically in contours, and the color actually explains the vorticity terms for a better representation. Now, so advection does not basically play a role here for northern propagation as we see, but the beta term, the negative beta term, leads positive rainfall anomalies during the strong convective events over Bay of Bengal by about 5 days, and this is not present over the Arabian Sea. So beta term is basically very essential for northern propagation over over Bay of Bengal. Now, this beta term basically creates an asymmetry in the meridional winds just near the center of the convection, which basically helps moisture anomalies to advect northward from the south side of the convection, and then pushes the convection to the north. And this has been shown theoretically by Young et al. In 2019. So beta term basically plays a role over Bay of Bengal. Now, if you look into the tilting and stretching term, now the top one is tilting. So tilting actually has a component over, shows signature over both the ocean basins, but it is stronger over Bay of Bengal. The color bar is it shows a stronger nature over the Bay of Bengal. Now, stretching has a very strong characteristics over the northern Arabian Sea, and it's kind of sets the environment for the faster propagation over the northern Bay of Bengal, and kind of breaks down that it shows the why the rainfall could be propagating much faster over this northern side of the Arabian Sea. Now this stretching basically is the convergence term, and which is not surprising that we can see that stretching and rainfall kind of go side by side. Now this shows the lead lag behavior of in the time series sense over both the ocean basins. Now if we look into the tilting term more deeply, I am not showing you all the details of the other terms, so just I will focus on the tilting term. That is because that is the most important term here. So the tilting term can be is comprised of 4 different terms. This one is the first term, del omega prime by del y, del u prime bar by del p, and that basically actually largely modulates the behavior of this entire tilting term. So if you just plot this term, it's basically this. It looks very similar as the entire tilting term. Now, looking into further into this term, this basically is consist of two different components. This one, the first component del omega prime del y, is the vertical meridional gradient of intraseasonal vertical velocity, and the second component, the del u bar by del p, is basically the vertical share of mean zonal winds. So if you just plot the vertical share of mean zonal winds, you can see that the vertical share of mean zonal winds that does not have a very different structure over both the ocean basins. But if we look into the propagation or the lead lag behavior of this del omega prime del y, or the meridional gradient of intraseasonal velocity, over Bay of Bengal, it shows a much stronger characteristics, and it is stretched vertically till up to 100 hectopascal level. So over Bay of Bengal, the del omega prime del y term is quite substantially significant than over Arabian Sea. Now, what does this term represent? This basically represents the basically the development of convection. The more convection you have, then the gradient of this omega intraseasonal vertical velocity will be much higher. So it says that over Bay of Bengal, we have a much stronger convection than over Arabian Sea, and this strong convection basically helps developing this tilting term over Bay of Bengal. So that's why we see a strong tilting term over Bay of Bengal. Now, if you come into the second term, this basically is associated with the Hadley cell circulation. This, because as this is del omega bar by del y, this is basically the Hadley term, Hadley circulation term. And if we look into the lead lag behavior of this term, then over Arabian Sea, this has a very strong characteristic, but it has a negative sign associated with it. So it basically negates the first the effects of the first dominant term. But again, this has a very negligible effect on the tilting term overall. Coming into the third term, this is basically the vertical shear of meridional winds, and this basically I have plotted the vertical share of mean meridional winds over the region, and it shows a very different characteristics over Arabian Sea and over Bay of Bengal. Now, if we plot this term with the negative sign over as a lead lag behavior, it shows that it has a very strong characteristics over Arabian Sea. Now, it is negative. It is showing negative because I have plotted with the negative sign here, which says that it is basically contributing towards the tilting term, and it has a much significant sign over the Arabian Sea as compared to Bay of Bengal. Now, this term basically, Dixit and Srinivasan has shown that the vertical share of meridional wind is important for the ISO phase speed. Now, using this term, we found out that this could be contributing to the much faster propagation speed over the Arabian Sea. So in summary, we have investigated the mechanism of northward propagation of convection over Arabian Sea and Bay of Bengal during boreal summer using vorticity budget equation. The tilting term leads precipitation maxima by about 6 to 8 days over Bay of Bengal and 2 to 3 days over Arabian Sea. And the meridional gradient of vertical velocity generates a positive tendency of vorticity to the north of an existing convection. In its negative values to the south of convection develops downdrafts and suppresses convection. This mechanism is much strong over Bay of Bengal, and the beta term is basically very important over Bay of Bengal. and not very important over Arabian Sea. That's where we found out. And over Arabian Sea, vertical shear of meridional winds play an important role over ISO propagation. Now, with this summary and conclusion, this can be concluded that organization of convection could be one of the key components to realistically simulate ISO in the models. Now, using this diagnostic, we are applying this diagnostic on the
Can
new.
you please conclude?
Yeah. This is I'm almost done. This is the last slide. So multi-physics, multi-model ensemble. So we have different convection schemes and microphysics schemes, and this basically gives 6 physics combinations. And we have developed, the IITM has developed a multi-physics, multi-model ensemble data. So we are planning to, and this is going to replace the next ERP version 1 extended range prediction in near future. So you're planning to, we have applying this diagnostic I presented here in the MPMME dataset to understand what basically drives the convection in the both ocean basins. So this work has been published yesterday in Climate Dynamics, and this is my contact. So if you find interesting in something interesting in the study, please contact me. I will pass on the published version of this work. With this, I will thank you very much for your attention, and I will take any questions you have.
Thank you, Dr. Nirupam, for your nice presentation on the investigation on the dynamics of the northward propagation of the convection in the Indian seas. If any question, we can have one question. If not, that let us move because we are running out of time. Next presentation is again by Professor Andrew Turner. So,
thank you. I will just share my PowerPoint.
yeah, please.
Yeah. Good. And if I make that full screen, can you see the full screen?
Yeah, now it is fine.
Yeah, excellent. Okay, I'll get started. So thank you very much. So this is about a project that's called the Orographic Rainfall Processes in India under the Improve project. This is a project that it had a funded component in the UK that funded University of Reading and University of Leeds, but we also had named partners in India under the Ministry of Earth Sciences Newton Fund agreement at IITM and IMD in Pune. And you can see the list of colleagues here on the project. And I'm just coordinating it. The other people here have done the work. So these were the people involved. It's actually a very short project. We didn't start until September 2019, and we're just finishing up this month. And we even had a funding gap in the middle as well. And the main work the main funded work has been done by Kieran Hunt, who's on the picture on the left up here, and Jayesh Fadter, who's up here. And our collaborators in India were Rajiv, Sachin, Subrata Kumar Das, and Utsav. Okay, so it's this map again that I showed you earlier, just to highlight that for orography in India, we were interested in 2 main regions. Of course, the Himalayas going up to 8,000 meters, and then the Western Ghats Mountains down the west coast. And what we wanted to do was to determine the drivers of typical and extreme orographic precipitation in the Western Ghats and Himalaya. So by typical, I mean just the general diurnal cycle. And of course, extremes, we all know there are orographic extremes of rainfall, things like the Uttarakhand floods that especially affect the Himalayas, but also the Western Ghats as well. So the Kerala floods of 2018, which lead to very large damages and loss of life and infrastructure and so on. So we want to determine how mechanisms of orographic precipitation and extremes are represented in models as well. And the models we were looking at were ranging from the convection permitting kilometer scales up to parameterized models. And we also wanted, if possible, to try and suggest what mechanisms might be missing from models at different scales. So what I'm going to do is I'm just going to give two examples of studies we've done in each of the two regions. I'll start with the Western Ghats. So this is some work that was led by Jayesh Fadter at University of Leeds. He's now working in the US. So this is looking at Western Ghats rainfall from a Froude number perspective. And we were motivated to start this work because of the Western Ghats rainfall regimes that I mentioned in the previous talk, in fact. And so what we found is that based on radiosonde data at different sites along the Western Ghats, you could classify the flow regime into different Froude number terciles, low Froude number cases on the far left here, and high Froude number cases on the far right here. And the particular example shown on the screen in this diagram is based on soundings from Mangalore, and the precipitation is from the IMS data. And the diagram at the top is just showing the rainfall anomaly in the different regimes. So you can see that there's quite a pronounced difference in the rainfall anomaly between the low Froude number case on the left and the high Froude number case on the right. And that really becomes pronounced when you look at the contribution of rainfall in those different regime days to the overall seasonal rainfall total. So especially the low Froude number regime contributes a lot of rainfall, up to about 60 or 70% over Southeast India, Tamil Nadu. So Jayesh has a paper on this that we've just recently submitted to the quarterly journal. And just some other aspects. I mean, it's something that works if you choose other sounding sites over the Western Ghats, to Mumbai, Goa, and Cochin as well. And one of the interesting things is, of course, that there is a large-scale control on this by bigger modes of variability, such as the BSISO. So this chart here just shows that your Froude number, which is on the left scale here, there's some preferences for different Froude numbers according to what phase of the BSISO that you are in. The other thing that we've noted, and this is just a cartoon from the paper, when the paper comes out, you can see it for a more detailed explanation, but the flow regime also strongly influences the diurnal cycle of circulation and convection over the Western Ghats. And our view of this is that in low Froude number regimes, you have quite a strong diurnal cycle between day and night, whereas in the high Froude number regimes, that convection is likely to be trapped much more over the Western Ghats Mountains. So that's quite an interesting finding. Another aspect of the Western Ghats study has been the development of an analytical two-layer model of the flow, a bit like a shallow water model. And the idea of this was to test the role of horizontal flow and stratification in each layer for perpendicular flow incident on a mountain ridge. And this, of course, approximates the monsoon flow approaching the Western Ghats Mountains, which are almost north-south. So this was work done by Stephen Griffiths and Andrew Ross at Leeds. And we're trying to answer the question, can different phases of convection near to the coast be driven by different flow structures? So this U as a function of Z, and particularly we were thinking about cases of uniform flow where the upper and lower layers of flow are in the same westerly direction, and then sheared flow, in which sense they are in opposing direction in this simplified case. And we look at the steady state linear responses to these types of flow in this analytical model. And we, as you can see in the diagrams, you can see quite different patterns of vertical velocity anomaly associated with that. But of course, what we need to do is to adapt this model to a more realistic setup that might include a rotating framework and non-hydrostatic and so on. And we aim to also follow up this work with more detailed process studies in the WRF model. So now moving on to just a couple of quick examples in the Himalaya. So this is a paper that was just accepted a few days ago in the quarterly journal, led by Kieran Hunt, with myself and Reinhard Schiemann. So understanding the twin diurnal rainfall peaks in the central Himalaya. And as you can see by the title of the paper at the bottom of the screen here, these are explained by two different processes, one of which is a katabatic process and the other is a convective processes. So if you were to just do a kind of a long-term mean of the diurnal cycle of the central Himalaya, you end up with two peaks. But these peaks are often not happening on the same days, so that's often a danger of using climatology. And if you start separating out the days, you tend to find that some days are favoured the peak at one time, the nocturnal peak, and others a daytime peak. And Kieran in his paper goes into some quite detailed understanding of the flows around the foothills of the Himalayas, their diurnal cycle, and how they variation between the different peaks. So please get in contact if you'd like a copy of that paper. Another study that Kieran has led, along with Professor Dimri of JNU, is looking at impacts associated with the strong rainfall in the Himalayan region, and this in particular was about landslides. And what we've done is looked at the relationship between occurrences of landslides and western disturbances, which of course are dominant in the winter period, and tropical depressions, monsoon depressions, which are of course dominant in the summer. And what we find is that the majority of landslides occur in the presence of one or other of these phenomena, such that western disturbances, they increase the likelihood of landslides in the Himalaya by strengthening the moist southwesterlies from the Arabian Sea, and tropical depressions increase the likelihood of landslides in the summer by either extending the monsoon trough further to the northwest up towards the foothills, or by enhancing a southeasterly barrier flow. And you can read more about that in this paper in Science of the Total Environment that came out last year. Other talks of interest this week, and especially tomorrow, related to improve. Sachin has been working with us on radar analysis using their Western Ghats site. Kieran Hunt has a talk tomorrow at roughly this time on how interactions between tropical depressions and western disturbances cause heavy precipitation. And we need to get an idea away from the idea that western disturbances are purely something that happens in wintertime. They can encroach into the summer, and especially in the shoulder seasons of the monsoon, they can have really quite strong impacts. And so probably tomorrow, Kieran will show you a diagram like this that tries to classify the interactions between western disturbances and tropical depressions into four different types. And Kieran has another talk tomorrow on modes of coastal precipitation over southwest India and their relationship to intraseasonal variability. So I alluded to this in my Encompass talk a few talks ago, and he will show and explain in more detail this diagram about how the BSISO controls these regimes. One of the other things we've been doing in Improve is to also work with Subrata in Sachin's group on again that radar analysis, and he has a talk tomorrow. So with that, I just thank you for your attention. I'm happy to take any questions either by email or in the chat, and yeah, thank you very much for your attention.
Thank you, Professor Andrew. If any question is there, we can have one or two questions. Otherwise, let us thank
There is a
Professor
YouTube
Andrew.
question.
Yeah, anything is there?
Sir, which parameterization scheme is best for orographic rainfall simulation?
True. I think he.
Sir, I think Professor Andrew has left the meeting.
Yeah.
So we can go to the next presentation.
Yeah. Let us go to the next presentation by Murali Nageshwar Rao. Can you share your presentation, Dr. Murali? Yeah, it's fine now. It's fine. Can start your presentation. Not audible. I think you are muted.
Go to the center top, one panel will come down and you can unmute yourself.
Yeah. Now it is audible?
Yeah, audible and it is full screen. Yeah, please
Yeah,
continue.
okay. Yeah. My topic is predictability of summer monsoon monthly rainfall and associated with the extreme rainfall events over Taiwan by using the NCEP Global Ensemble Forecast System version 12 model. And I am very much thankful to my team members, Dr. Vijay Talapragade and Yojan. And my teamwork is well recognized at Anchor UCAR system and at NOVA. And we got recognized, myself and Dr. Vijay also, with some awards, special recognition awards. And my main motto of doing this work, it is well known the skillful prediction of the monthly scale rainfall at a small regions like Taiwan is the one of the challenges of the meteorological scientific community. And present existing forecasting systems across the world can simulate the year-to-year variations within the seasonal rainfall. But however, month-to-month variability during a year, it is still challenging. Particularly, Taiwan is one of the subtropical island in Asia, and it experiences rainfall extremes regularly and leading to landslides and flash floods in and near mountains and flooding over the low-lying plains, and particularly during the summer monsoon from June to September. And although Taiwan is the lot of water scarcity due to the steep topography that hardly hold the rainwater, and it is the 18th rank of the water scarcity country of the world. Therefore, there is a high demand for the monthly scale rainfall and associated extremes over this region. And it is recently in the September 2020, NOVA NCEP has implemented Global Ensemble Forecast System version Model 12 to support to the stakeholders and for sub-seasonal forecast and hydrological applications. And this model data, consistent reforecast data of this model data is available from the 2000 to 2019. And this data is initialized at 00 UTC once per day out to 16 days lead time with 5 ensemble members, except Wednesday when integration is extended to the up to 35 days with 11 members. So this model data I have available for the monthly scale up to 35 days. That's why I have considered this model data for the monthly analysis by using the weekly ones initial conditions with 11 members. This model data is up to 10 days. It is available horizontal resolution 0.25 by 0.25 and with 3 hourly accumulated. Later on day 10 to day 35, it is the 0.5 by 0.5 spatial resolution and 6 hourly accumulation. And in this study, we have considered that 11 members. And this data have evaluated against the CMORPH analysis. And also we have used the benchmark data, Global Ensemble Forecast System subjects experiment data with the same resolution, spatial resolution, and same weekly initial conditions with the 11 members in the same reforecast period. And it is well known, any model raw model product, it is not directly useful to apply. So a lot of systematic bias it is there. So it is need to some post-processing methods. In this study, we are implemented the quantile mapping method. This technique mainly used for the correct to the model predictor rainfall to the mapping onto the observed rainfall distribution. This process also called simply histogram equalization or rank matching method. In this quantile mapping method, we are assuming the gamma probability distributions of the observed and forecasted values are used. The quantile mapping method, the bias is not calculated explicitly. Suppose the CDF of the observation and forecast we know, the particular day forecast, raw forecast we know, we can correct that using that CDFs. This is the F inverse observation is the observed cumulative distribution, inverse distribution, and F bar it is the forecast distribution. This is the forecast the particular day. Then we can get that. And mainly this map, it is working transformation between the two CDFs, observed and forecast. The entire process we have used leave-or-not cross validation way to apply for the operational. It is easy to apply for the operational. So before going to do evaluation of the present Global Ensemble Forecast System version model, we are compared with that GFS SubX model. And before going to actually the East Asian Summer Monsoon Index, it is the good potential predictor. And it is strongly associated with the East Asian Summer Monsoon climate anomalies like temperature and rainfall. So we need to know what is the capability in predicting the East Asian summer monsoon index, which is a potential predictor for the East Asian summer monsoon. So in this study, we have considered that index from that NCEP 20th century NCEP real analysis index, and we can calculate the index from the GFS sub-X and GFS version 12 model, and we have done some performance evaluation. Then here it is clearly you can see the improvement in the latest update model, GFS version 12 model. Even the RMS is decreased lot as compared to the sub-X model, and correlation coefficient also it is increased slightly, and index of agreement also it is increased. But in both the models, the skill is decreasing and error is increasing with the lead time. But as compared to sub-X, the GF latest model, it is good slightly, and it is mainly occurred the improvement in the prediction skill of the GFS V1 mainly attributed to the combined influence of the better initial conditions in the model, and more advanced microphysics schemes also used, and finer resolution also it is there, and a new finite value dynamical core system also there. So these all are, it is affected to the increase the model skill, prediction skill in the GFS version 12 model. And later on, I have seen the performance of the comparison in both the models for the East Taiwan or rainfall. We can see in the mean bias, it is less in the GFS version 12 model as compared to the sub-X, and even RMS also it is less, and correlation coefficient also slightly it is increased, and index of agreement also it is increased. And however, the skill in both the models, it is decreasing with the lead time. It is obviously it is there, and even you can see in the probabilistic ensemble forecasting skill, prediction skill also we can we are obtained for the wet days and year days, extreme rainfall days on monthly scale. Then the slight improvement, it is clearly reflected in these ROC curves for all the months for wet days and both extreme rainfall days. And later on, I have implemented that on the latest model for improve the prediction skill and the calibration method by using the quantile mapping method. This is the spatial distribution of rainfall. This is the first one is the observation as considered for the CMOF, and this is the raw product, second row, and the third one is the calibrated forecast. We can see the raw forecast as GFS model is well in capturing the all climatological features, spatial patterns, climatology, and interannual variability also, CV also it is well captured. But it is the magnitude is large wet bias it is there, but after calibration the wet bias significantly it is reduced, and the patterns as similar to the realistic, and interannual variability also in the raw product it is less as compared to the observation. But after calibration method, it is the interannual variability it is increased a lot. And the CDF form, the probability distribution, you can see the distribution curve, CDF curve, it is far away from the observation, but after calibration, it is both are it is overlapped. It is near to calibrated one, it is near to the observation for all the months. And in this curve, clearly you can see the number of wet days, it is more for the raw model product as compared to the observation, and extreme events is very less. The probability is very less. So after calibration, the distribution of the various intensity rainfall events, it is well adjusted to the observation. And this is the root mean square error. You can see the root mean square error in the raw model product, it is more across the country, but after calibration, it is significantly it is reduced. But still, it is more where the prominent rainfall it is occurred in the southern part and eastern part, and it is decreasing to the north to westward. And mean bias it is too large, wet bias it is too high, but after calibration it is near to zero for all the months. And the correlation coefficient it is good for the particularly in the August and June, but it is not that much affected the calibration method. It is similar to same. It is as usual. It is same to the raw model product, but the index of agreement it is significantly increased for across the country for all the months. And this is the spatial distribution of the various wet days and extreme rainfall events. Here, extreme events we have considered for the greater than 5 centimeters, and this is the wet days we have considered for the greater than equal to 2.5 millimeter per day. When you are compared with the observation, the raw model product, it have the wet days is overestimation of the wet days large, and we are also consider for the each member and frequency average of the frequency of the all the members also we have compared. That one it is slightly it is less, but after calibration method, it is the spatial patterns of the wet days and as well as the year days it is increased. In the wet days case, it is the overestimation, while it is the underestimation for the year extreme rainfall days. But particularly the extreme rainfall days after calibration, it is well captured, which is the leads to the flood situations, and it is highly risk to those regions. So this prediction is very useful for those cases. And we are also done some categorical statistical skill scores like accuracy, POD, and false alarm rate, success ratio, and equitable thread score, and those things we have done. Here I have presented the ETS. We can see the ETS is compared to the ensemble mean, the individual members, mean of the individual members, it is slightly it is better. But after calibration, both the cases, ensemble mean calibration and each individual members calibration, then we can take the mean. Then in the both the cases, a lot of improvement. Our calibration method, it is improved. A lot of improvement it is there, particularly for the wet days. The same we can observe for the extreme rainfall events, but as compared to the wet days, the skill is still it is low, but it is significant improvement it is there as compared to the raw products. And this is the performance diagram, which is described for the all the skill scores, all the categorical skill scores. And here we can see this based on the performance diagram, the raw model product have high POD because for wet days high POD it is there because every day it shows the wet days. That's why it shows high POD. But other skill scores like success ratio and thread score and frequency bias, it is very low. But after calibration, those skill scores, it is significantly it is increasing, and the raw model after calibration, all the months forecast, it is near to the diagonal, and it is significantly it is improved. Only the POD is decreased because the number of wet days it is significantly it is reduced due to this method. But in the case of extreme rainfall days, the POD also it is less, all the skill scores also it is less. But after implementing the calibration method, it is almost near to the diagonal, and all the skill scores it is significantly it is improved. So the calibration method it is improved for the particularly various intensity rainfall events. And we have also done for the prediction skill of the probabilistic forecast, ensemble probabilistic forecast, and particularly this RPSS skill score for the wet days and extreme rainfall days. You can see after calibration, all the months, the RPSS skill score, it is significantly, remarkably, it is increased across the country. Even RPSS skill also, it is increased for the extreme rainfall events. But when compared with the wet days, year days skill score, it is less because the sample size of the wet days, it will, extreme rainfall days, it is less. So this work is already it is accepted in the weather and forecasting. So these are my summary and conclusion. The major remarkable improvement in the prediction skill of the GFS as compared to the SURVEX. This improvement may be attributed to the combined influence of the better initial conditions, more advanced microphysics schemes, finer resolution, and finite volume 3 dynamical core. And the raw GFS is able to capture all the climatological features, climatological mean, interannual variability, and coefficient of variation, and all the things. But some limitations it is there for the magnitude of the rainfall and interannual variability. But after calibration method, those climatological features, it is similar to the observation. The RM is also significantly decreased, and skill scores also significantly increased after calibration. The correlation coefficient and index of agreement, it is greater than 0.8 after calibration. And after calibration, the wet days also it is decreased, and remarkably it is increased the extreme rainfall events after calibration, which is highly useful for the making plans for the disaster management of this region. And yeah, all the categorical skill scores also it is remarkably it is increased, except for the probability of detection for the wet days. So this assessment of the probabilistic analysis, probabilistic forecast reverse also After calibration, the ensemble forecast, the ensemble probabilistic forecast skill scores also it is significantly improved. While before in the raw product, the skill is less than the climatological forecast. So the lot of improvement it is there. Our main motto, our further research scope is we are going to implement some machine learning things. Thank you for your attention. Please let
Thank
me
you
know.
very much, Dr. Murali,
Yes, sir.
for your nice presentation of this award-winning study.
Yes, sir.
So, I think if any question is there, we can have it. Maybe one question. Already we are running out of time. Otherwise, let us thank Murali again, and
Yes,
let
sir.
us move to the next presentation.
Thank you.
By
Thank you.
Dr.
Thank you, sir. Yes, sir.
Sandeep
I really thanks to my
Narayana
team
Sethi.
members to support to this entire study.
Okay.
Yes, sir.
Thank you very much.
Thank
Yeah,
you.
please,
Thank you.
please share your presentation, Dr. Sandeep.
Sir, is the presentation visible? Am I audible?
Yeah, it is visible and audible.
Yeah, sure. Myself, I'm Sandeep Narayan Sethi. I'm working at Indian Institute of Tropical Meteorology. I'll be talking on the topic South Asian monsoons response to weakening of Atlantic meridional overturning circulation in a warming climate. Before going further, I would like to make a comment on the so far understanding of the Atlantic meridional overturning circulation, or AMOC, and its possible global climate impacts. AMOC is one of the major branches of the thermohaline circulation, which is solely responsible for transferring around 25% of the heat and salt water from the equator or tropics to the poles, wherein this heat is released into the atmosphere there, and the cold water and the salty water, which is denser, which sinks and forms the equatorward branch. This branch in the Atlantic, we call it AMOC, or Atlantic Meridian Overturning Circulation. AMOC has its own variability with periods or stronger periods of having a stronger variability and also weaker variability. We have seen from the 1200-year proxy data from transatlantic basin that there are few hundreds of years where AMOC was relatively stronger. That implies the ocean heat transport from the tropics to the poles was higher when compared to certain periods where in little ice age we see that there is a weakening of the Atlantic meridional overturning circulation. We've tried to understand whether this weakening or strengthening of AMOC has anything to do with South Asian summer monsoon. So we tried to check it with the Sahia Cave rainfall data, which is available during the 1200 years of analysis which we have done over the Atlantic, and we found that positive correlation of 0.45, which is at 90% at 95% significance level. So in order to understand the mechanism, we tried to use a suite of experiments and also IITM ESM to understand the mechanism, which I will be presenting in the consecutive slides. When it comes to a stronger AMOC, we have seen that there is a northward shift of ITCC, and also when there is a weak AMOC, or the weakened heat transport towards the poles from the tropics, we saw a southward shift of ITCC. In order to understand this further, we performed a suite of experiments. And also in the late 21st century, we have seen that the proxy reconstructed data also shows a sharp decline in the strength of AMOC just in the 21st century alone. This has been attributed to the Arctic sea ice melt, which is happening more in the recent decades. This exposes the ocean to anomalous surface heat and freshwater fluxes, resulting in a positive buoyancy anomaly, and that it can affect ocean circulation. And also the in situ observations at 26.5 degree north in the Atlantic also shows from 2005 there is a considerable decline in the AMOC. Also, IPCC AR6 has shown that there will be almost 5 to 6 groups decline in AMOC in a future warming scenario under various shared socio-economic pathways. Also, the September sea ice extent from IPCC AR6 report suggests that based on a plethora of models and a multi-model ensemble shows that from 2050 to 2060, between this particular decade, there might be a completely September sea ice area free Arctic. So in the background of this, we try to understand what is the association between AMOC and South Asian monsoon, and whether this relationship is going to change in the future on the background of declining AMOC and also vanishing Arctic. So we had to use a model in which both the South Asian monsoon characteristics and also the Atlantic meridian overturning circulation are very well represented. So we have chosen IITM-ESM, in which both the characteristics of AMOC and global precipitation were reasonably well simulated. Also, the 300-year pre-industrial controls from AMOC, the red line over here shows almost 17 to 18 square groups of AMOC, which is stable, having its own multi-decadal variability. To achieve this kind of strength of AMOC, we tried to improve the energy balance, which actually resulted in the reduced Arctic sea ice, which also influences the strength of AMOC, and that's how we got an improved AMOC strength in the model. Now that we have a model which represents both AMOC and the South Asian monsoon characteristics very well, we had to adapt an experiment strategy wherein we actually delineate or just take out the strength of AMOC or weaken the AMOC alone without changing any other factors, and try to understand whether it really impacts the South Asian monsoon. So we have chosen one of the model intercomparison projects, that is flux anomaly forcing model intercomparison project from Gregory et al. And they have formulated this particular strategy, and it is actually recognized as one of the WCRP grand sea level change, WCRP grand challenges for sea level increase. So here I have introduced two new tracers into the model, which are redistributed heat and the added heat. Redistributed heat is just a passive tracer. It doesn't affect density. It actually gets transported similar to theta, that is the potential temperature, but it doesn't feel the perturbation. Wherein the added heat feels the entire perturbation. The entire trick in this particular method is the atmosphere feels the redistributed heat, not the potential temperature, not the TA. So this redistributed heat is just the effect from the ocean circulation alone. Also, they have given us surface heat flux anomalies and the precipitation minus evaporation anomalies as a forcing, which has to be incorporated in the model. And this forcing will be common among all the models which participate in FAF-MIP or flux anomaly forcing MIP. So this gives us one of the ideas that if all the models use the same forcing, and what will be the strength of AMOC weakening, and also what will be its global climate impacts possible, can be studied. So then we have seen that from FAF heat experiment, we have seen that AMOC has declined almost 50%. If you see here, the blue line is the control simulation, the red line shows the FAF heat, and the green line shows the FAF water, that is only freshening, that is imposing only precipitation minus evaporation, and red line indicates the heating. So then we see that in the FAF heat, there is a large scale weakening, almost 50% weakening in the strength of AMOC, and FAF water, which also shows around 25 to 30% weakening. This weakening of AMOC is attributed to the enhanced Arctic sea ice loss because of the imposing of surface heat flux anomalies. Also, because of this fresh water, which actually exerts into the Atlantic, there is a weakening of potential density. Likewise, it's becoming more buoyant, and the stratified column, which will affect the ocean circulation. Because AMOC is weakening, we expect that the poleward ocean heat transport will weaken. The climatological poleward heat transport is represented here. The atmospheric heat transport is in the red curve, and the blue curve is the ocean. And when we impose these FAF heat anomalies, we found that there is a change in oceanic heat transport. That oceanic heat transport is becoming weaker but obviously that the AMOC is getting weaker. In an idealistic situation where if ocean is not transporting heat from the tropics to the poles, atmosphere takes it up and atmosphere does the necessary. And this has been documented by Donoho et al. In 2013. They proposed a mechanism that atmospheric heat transport is a response to whatever happens in the ocean heat transport, and this atmospheric heat transport at the equator will determine the strength and the location of ITCC. So they have shown that whenever the AHT at the equator is northward, the ITCC shifts towards the south. So following the same philosophy, here we understand because at the equator we found there's a positive at AHT, we found there is a southward shift of ITCC. And also, because there is a large-scale weakening of the heat transport, we see the interhemispherical SST gradient also shows a weakening, and this large-scale north-south interhemispherical temperature gradient can also influence the global Hadley cell, monsoon Hadley cell, also. And there is a 850 HPA to 200 HPA thermal gradient also weakened because of this. And because of the global Hadley cell and the monsoon Hadley cell weakening, we found there is a weakening of circulation and precipitation of the South Asian monsoon just by declining AMOC alone in this particular experiment. But this is an ideal case. Also, along with the heating, the GHGs are also increasing. In this particular experiment, the GHGs were not considered. So what happens in a realistic scenario? There comes the second point, wherein we have changed the carbon dioxide concentrations up to by 1%, and we reach it by 70 years, it becomes 2 times the carbon dioxide concentration. So that is taken as the experiment, and when related to the pre-industrial control, we formulated the same thing and we tried to understand the mechanism which we have proposed in an ideal scenario. We found that the ocean heat transport, atmospheric heat transport were exactly behaving as expected. That the ocean heat transport is weakening, the atmospheric heat transport is enhancing, the interhemispherical SST gradient is also weakening, the 850 to 200 HPA temperature gradient is also weakening, therein the circulation is weakening, but the precipitation was enhancing in a future warming scenario. So then we understood that the precipitation is actually governed by thermodynamic balance rather than the dynamic balance. So then we tried to understand this further. We have seen the 850 HPA moisture flux, moist static energy, divergent component of moisture transport, and when we concluded that moisture transport or the enhanced moisture holding capacity of the atmosphere in an extreme warming scenario will play a major role rather than the ideal scenario where AMOC is declining. So we found that there are 2 novel aspects in this current study. Firstly, we distinguish the process of AMOC weakening quantitatively by imposing surface heat fluxes and freshwater fluxes individually. We find an enhanced weakening of AMOC in FAF heat rather than FAF water, indicating the importance of heat flux. Most of the previous studies were not addressing the importance of heating. They always study the AMOC weakening in the background of freshening only. The second novel aspect of our studies, with a suite of experiments, we demonstrated that the South Asian monsoon circulation weakens in response to weakening AMOC, while precipitation changes are dominated majorly by the thermodynamic response. So we finally conclude that thermodynamic component of the water budget plays a major role in driving the South Asian monsoon in a future warming scenario, in spite of a decline in the strength of AMOC. But the major question still stays that not only Arctic sea ice, but in a future warming scenario, there is a projection of the Greenland land ice melt as well. So we started building the efforts in the future scope that melting on the Greenland in the coming decades could contribute to this further weakening. So the time history of the Greenland meltwater runoff is not included as a forcing in any of the CMIP-5 multi-model ensemble. We started in-house to try to include this Greenland land ice melt into IITM-ESM. We have chosen CISM, the community ice sheet model. We have done the simulation for 45,000 years for the standalone version, and we reached a 10,000 year steady state from this model, and also surface mass balance is pretty much stable. So going ahead, we would like to incorporate this land ice model into IITM-ESM in order to better understand the changes of the glacial ice and its possible impact on the AMOC. Thank you, everyone. That's the presentation.
Thank you, Dr. Sandeep,
Yes, sir.
for your nice presentation on this interesting topic. If any question is there, we can. If not, let us again thank all the speakers for their excellent presentation and the sharing the very novel results. Thank you very much. And I think over to the organizers.
Thank you, Dr. John. Thank you nicely coordinating the whole session, as well as thank you to all speakers, whoever presented here in this session. And hopefully the whole interaction will continue also after this session throughout this workshop. So today, goodbye to all. So have a nice day, night, or good night.
Good night.
Thank you, sir.
Night
We'll
or
be joining tomorrow
morning
again.
or good evening.
Yeah.
Thank you.
Good night.
Thank you.
Thank you.